Hope everyone's doing well. We're going to give our brothers time to get in. So I think class officially starts in right at about a minute. Let me see if I can pull up my second hand. So give everybody a minute to get in. We should be able to rock and roll and get started pretty much on time today. Hopefully everybody is able to vote. Was able to vote did vote, okay? And you're someplace safe and just get through this purge. Get through this election, okay? Bad joke, scary joke. Yeah, these movies kind of wig me out a little bit though. Like I feel like they be premonitions or foreshadowing. A lot. That science fact starts as science fiction. Science fiction is a precursor to science fact. So, you know, I intentionally don't watch certain things because of those reasons. I'm like, I'm good on purge and stuff like that. I try to keep that kind of stuff to a minimum. But yeah, hopefully everybody has made their decisions and got their stuff in, and hopefully America will survive. I'm not really. It's just feeding into the hype and just having some fun, really. I think everything will be okay. Not to say that there won't be growing pains. I think there will be growing pains, but I think ultimately everything will be fine. Give everybody like 45 more seconds. Let's see this one. Well, that's strange. Or maybe I'm just not looking at it right. Okay. Well, I do have that it is that time. So we'll just go ahead and get started, and we'll give people more time to get in, and we'll just let them in as they arise. But we'll go ahead and get started since I have that it is that time. I think I got my timing down for this event, for this kind of presentation or whatever. Let me see. Let's go ahead. Maybe I should just leave this open for right now. This is. That's all right. Okay. Let's see. So, let me check one other thing. I can close this out. Let's just move this over to the side. Okay. Maybe I can. Gotta let him in already. Right, let's just put this like about here. And we'll go like this. And if I can just shrink this down some as well. Maybe move this over here. Move this right here. And then this can go like about here. Okay. So no major announcements. This is I think this is week 12, right? So what that means, exam 3 should open up Wednesday night. So tonight at midnight, it should open up. It should be available for full credit from tonight at midnight until Saturday at midnight. You can still submit it after Saturday, but it's a 10% late penalty. And pretty much your grade, whatever grade you see on Pearson, that's essentially how the grade is. I probably will go back and scale things to kind of match what's over in syllabus. So I think the exams might have a heavier weight, and the homework and quizzes might have a lesser weight. That's the only difference, right? But essentially, what you see in Pearson is what you get. And again, I'm gonna scale those things to kind of match the way it is in Pearson. Let me see. We have this gentleman. All right, so yeah, other than that, I can't think of any real announcements. We are entering the home stretch. So I think for exams 1 and 2, what I did was during this week, we took this time to review and prep and things of that nature for the exam. So if this is week 12, I think we wrap up everything in week 14. I think we have 2 full weeks left remaining, right? So the main name of the game for my class, just make sure Pearson is in order. You definitely want to maximize the scores on your exams first. Once your exams are in order, that's the bulk of your grade. That should be the bulk of it. Homework and quizzes are just kind of fillers, but most of the grade comes from exams. Let's go ahead and let. So yeah, you just definitely want to make sure that's in order. And so what I'm going to do, instead of this week of preparing for exam 3, I'm going to go ahead and take this week to try to go ahead and finish our lectures, right? So we have 2 sections remaining. Let's see. We have 2 sections remaining, section 3.1 and section 6.4. So we'll take time. We'll probably this week, we'll probably just do section 3.1. I think we're going to need today and Thursday to do that. And then we'll go ahead and knock out 6.4 in the probably next week. And anytime we have remaining, we can use to review old assignments, make sure things are getting submitted. If you want to ask questions from any assignment you're working on, any assignment you're working on, you can ask questions. But let's finish our lecture, and then the final exam is going to be cumulative, so everything from the beginning until end. Okay. Again, I am monitoring the chat, and let's get the party started. Okay. So in chapter 3, we only have time to go through 1 section, so we're going to be going through section 3.1 exponential functions. Okay. So a function of the form. Let's do this. Thank you. Thank you. I have a little different system working out here. It seems like it's okay. So a function of the form f of x equals a to the power of x. Let's see, I know who that is. Okay. Okay. Awesome sauce. If I could just shrink this down, that's the only thing I need to do to make it better. Anyway. Let's see, yeah. So function of this form, f of x equals a to the x, where the base of the exponent is positive and not equal to 1. This is called an exponential function with base a and exponent x. And the domain of exponentials is all rows, right? So we have these examples. We're going to introduce exponentials next Tuesday. Did I get that wrong? It could be. Give me a second, because that's a good question. I want to make sure that I don't have my dates incorrect. Let me do a quick. Let me ask real quick. Hang tight for a moment. That is a good question, because I just want to be sure that I'm looking at this properly. Let's go. Right. Yeah. Give me just a moment. Let's do this. Hey Siri, call Dr. Cooper on speaker.
Calling Dr. Dwayne Cooper. Mobile on speaker.
Hello, this is Dwayne. You can leave a message after the tone.
At the tone, please record your message. When you have finished recording, you may hang up or press 1 for more options.
Greetings, Dr. Cooper. I hope this message finds you well. So we just started our class today. This is like Tuesday at 2:25 on November 3rd, Election Day. One of the students asked, is our last class next Tuesday? So I was just calling to confirm the actual dates, the final dates of the class. I'm under the impression that this is like week 12. Then we have like all of next week, and then I thought it ended the following week, in like week 14. But I'm just trying to confirm like the last class, like when's the last time that we meet with the students? If you could like text me back, that'll be fine. All right, again, thanks for everything. Hope this message finds you well. Take care. See ya. All right, so let's do. Did I start the stream? Ooh, that was close. Okay. So we're gonna resume share. Unmute. Okay. So, oh yeah, I know. Yeah, I intentionally muted. I made a phone call, so I was just calling my supervisor to kind of confirm. He's gonna have to get back to me. He didn't answer, so I left a message. Let me let this other brother in, and I'll update everybody. So if I get an updated something that's different than what I said, then I'll let you know. Okay. Let me see. So otherwise, we're gonna kind of press forward. In any regards, though, our stuff is automatic on Mood on our Pearson, so it's there. We just have to kind of do it. Um, yeah, let me kind of try to get through these sections. Hold it. Did not mean to say his last name, but that's okay. Too late now. All right, now I'm gonna try something else. Maybe I can put it here at the bottom. Maybe that'll work. Ooh. Okay. I can get rid of it. It's fine because it's kind of annoying now. So we're gonna Saturday start on the 12th. Let me see. That might be right. I think that sounds right. If today, so next week will be what, the 10th. That 12th is that Thursday. That's next week, right? And then the following week should be the final, which is pretty much what we're doing. That sounds about right. Again, I'll confirm some dates with my supervisor. And it sounds like we're the same. It's just our philosophies were a little bit different, but essentially it's the same. Okay, so let's look at this. So we're going to, again, we only have 2 sections remaining, so we're pretty much on track. So we're going to introduce exponentials by evaluating them, right? So this first one, we have 3 to the power of x minus 2. So then f of 4 is going to be 3 to the power of 4 minus 2. So that's going to be 9, right? 3 squared is 9. The next one, the x is to do g of negative 2. So if we plug negative 2 into that function, we have negative 2 times 10 to the power of negative 2, all right? So that's the same as negative 2 divided by 100. A negative exponent causes it to go to the denominator, all right? It pushes it down. So then 2 divided by 100 is 0.02, negative 0.02. Bond, James Bond. 0.0. Trying to do 00. Anyway, 002, 007. Anyway. So then the next one, we're going to do 1 over 9 to the power of negative 3 halves, right? So there's a couple of dynamics going on here. Let's see. So if we address the negative first, we'll get 1 over 1 over 9. We can actually do it like this, to the power of 3 halves, right? So then that becomes 9 to the power of 3 halves. So that denominator in the exponent, that means square root. So that's going to be the same as the square root of 9 cubed. And I think that answer is 27. Okay, so we did several things there. And then that last example is a calculator example. We would use our calculator, right? So you definitely want to practice to make sure that you can plug this one into the calculator and do it properly. And we could check all of these with the calculator. For the sake of time, I'm going to kind of press forward because I don't know what our time looks like. So here we have a typed version of everything we just did. So you see 3 to the 4 minus 2 becomes 3 squared, and then that's 9, right? I think we got the same thing here. You see this one. And this one, if we put it in the calculator, you just want to make sure that you can generate this result. Okay? So then we're asked to graph this exponential, right? So what we're going to do, we're going to choose values of x, find the corresponding y. So we're just going to plot several points. So we're going to say x versus y. We're going to make a table. Let's do x. Let's start with negative 3. Negative 3, negative 2, negative 1, 0, 1, 2, and 3. Okay? And let's start with x when x is 0. So when x is 0, we're going to have 3 to the power of 0, which is 1. When x is 1, that's going to be a 3. 3 squared is 9. 3 to the 3 is 27. Oh, it's 27. Kind of did a combination of what I was thinking with what I was saying, and it was just not there. Let's see. I thought I let him know. He may have got booted. Let me just check. I think this is in order in which I admitted students. Okay, so he's in there already. Okay. All right. So I just realized, like I saw a notification like earlier in the month, Morehouse did something on like I guess it was virtual homecoming. Like it's so weird. Like that's like the peak of the HBCU experience, like homecoming events. Like that was so much fun. I mean, honestly, the whole experience is fun. It's whatever you make it. It's hard though. I ain't gonna lie. It's hard. Like it's just not easy, but you find a way. Like as long as you make up your mind and you just don't quit, you find a way. Everybody finds a way, and the experience is what you make it. You know, the experience is whatever you make it. But I know I traveled. Like when I was in Morehouse, like I went to Costa Rica. I was in Costa Rica for a month one summer. Just like I just scrambled some money together. Because my elders at that time, they were like, "Yo, if you want to travel," that's exactly how they said, "Hey, yo, kid, if you want to travel." But they were like, "If you want to travel, the best time is as an undergrad. As you become an adult and you get out of school and you start acquiring responsibilities, it's a lot harder to travel." So I just pulled some money together and went. I had a good time. Like I intently did things just to have fun, because it's enough of everybody trying to vie for my time and no fun. But yeah. So when x is -1, then again the negative forces it to the denominator. So then we get 1 over 3, 1 over 9, and 1 over 27, right? So then if we were to plot these points, I'm just going to do a rough sketch. Positive x is in this way. This direction, positive y is in this direction. This is just a rough sketch, but we can plot those points. I'm just kind of going like this, all right? That's essentially the graph that we get if we were to plot those x versus y's. Okay. So we see this table. I think they got the same results that we got. Then if you plot the x versus the y's, we'll get something like this. And then connecting with the smooth curve. Oops, I totally did mine backwards. I just realized I did exponential decay. So sorry, this one's going to be like this. Start here and then take off. Trying to move too fast, but that's the idea is there. Totally messed that one up, right? Plot the points, connecting with the smooth curve. I hope I didn't do that with my earlier students. I totally may have. Oh, I'm totally not here right now. Okay, especially the closer we get to the holidays, I just like blank out mentally. I totally do not. I just be kind of like saying what I know I'm supposed to say, but I don't do that. This one, same thing, right? We want to sketch the graph. I usually like to do 4, but it usually goes off the chart. So let's do -3, -2, -1. I'll put 0 here. 1, 2, and 3. Right? And then when x is 0, I think we still get 1. Let's do when x is -1, we get 2, then we get 4, and we get 8. The other direction is going to be a half, a quarter, and then an eighth, right? So now, if we, again, positive y is in this direction, positive x is in this direction, and this one does behave like exponential decay. Okay. Again, if we were to plot the x versus y's, it should look something like this. So you see the table, a computer to generate a table, and then we have a graph. Just get rid of this because I'm writing now. All right, rocking and rolling. You still working? Okay. Okay. So then we have some properties of exponentials. I'm just going to kind of touch on these. So again, we have an exponential function of base a to the power of x, where the base is positive and not equal to 1. The domain of an exponential is all reals. The range of an exponential goes from 0 to infinity. Okay. The entire graph lies above the x-axis. The x-axis actually serves as a horizontal asymptote. We get infinitesimally close to the x-axis, but we actually never touch it. A is called the growth factor of the exponential if A is positive. So as we take one step in the x direction, the y value increases by a factor of A. And if A is greater than 1, then it's called the growth factor. Okay? So that's going to generate an increasing function. And as x goes to infinity, y goes to infinity. As x goes to the far left, y goes to 0. Right? Okay, that was like the first example we did today. And then this next one, if a is between 0 and 1, that's called the decay factor. Okay, so then that's like the second example that we did. So it's going to generate a decreasing function. It's going to fall as we go to the right. As x goes to the far left, y goes off to infinity. As x goes to the far right, y goes to 0. That's when a is between 0 and 1. Each exponential is 1 to 1. 1 to 1 means that there are several terms that we use interchangeably when we're talking about 1 to 1. 1-to-1 is the same as has an inverse, which is the same as passes the horizontal line test, which is the same as every y corresponds to exactly 1x and every x corresponds to exactly 1y. Yeah, so all those terms that I just rattled off, we kind of use them interchangeably. So because exponential functions are 1-to-1, if one exponential is equal to another, then we can essentially equate their exponents, right? And again, being 1-to-1 means that the function has an inverse. Okay. And again, I'm just touching on these. I want to say that a lot of these notions naturally come out as we start working examples. The exponential function has no x-intercepts, so it never crosses the x-axis. Okay. The graph of an exponential is a smooth, continuous curve, and it passes through these key points, namely when x is -1, 0, and 1. Right? Those are the key points. Again, the x-axis serves as a horizontal asymptote for the exponential. If we were to multiply the inside by a negative, it's going to flip over the y-axis, and we'll have exponential decay. Okay. So one application of our exponentials we want to introduce it in this notion of interest rates, right? That's going to be the percent charge for the use of a principal for a given period. The interest rate denoted by R is expressed as a decimal. Unless stated otherwise, the period is assumed to be 1 year, and R is going to be the annual rate. Okay, and so we're going to introduce interest with this. The lowest form of interest we have is simple interest. Okay, so simple interest is given by this: I equals PRT, where P is going to be the principal, so that's our starting amount. R is going to be the rate expressed as a decimal, and T is going to be the time with the units of years. The units there are years. Okay. So we have Juanita has deposited $8,000 in the bank for 5 years at a simple interest rate of 6%. How much interest will she receive? Okay. So for part A, the interest earned again is going to be PRT. Okay. Where P is the principal, that's going to be $8,000. The rate as a decimal, 6% as a decimal is going to be 0.06. And the time in years is 5 years, right? So then we get the following. Hey Siri, what's 8,000 times 0.06 times 5?
8,000 times 0.06 times 5 is 2,400.
Okay, so after 5 years, the account has grown by that much. Okay. And then how much money will be in her account at the end of 5 years? So then for B, the future amount is going to be her starting amount plus the interest earned, right? So that's going to be the $8,000 plus the $2,400 to give us $10,400. That's not. There it is. Okay. Somebody coming in? What are you screaming for? You just got to hear your voice. I think my dog has Tourette's for dogs. Because she nothing has changed. She just losing her mind for no reason. Unless she can just see something I can't. She needs a bath too. She stinks. Anyway, okay. And it's I'd be kind of torn because I know you're not supposed to bathe them more than once a month, but she'd be needing it after 2 days. I'm like, man, why do you stink? So we'll figure something out there. All right. So I think we got all of these results, right? So then let's see. So compound interest is going to be the interest paid on both the principal and the accrued interest, right? Interest that is compounded annually is paid once a year. For interest compounded annually, the amount A in the account after 2 years is given by this, right? So the next level of interest that we have to discuss is compound interest. Yeah, there's some stories I like to tell here, but for the sake of time, we're going to let it be. So Juanita has her $8,000 in her bank account. It still has a 6% compounded annually for 5 years. How much will she have in her account after 5 years? Okay. I'm probably gonna use an augmented formula from what we just saw. Let me see. So A, the future amount is going to be P times 1 plus R over N to the power of NT, where N is going to be the number of compoundings per year. So if you, in this case, if we let n be 1, I think we'll get the formula we had on the previous slide. But I'm just going to use this, right? So her future amount, the principal was $8,000, so she started with $8,000. 1 plus the rate was 6% as a decimal, 0.06 divided by. Let me see. It's every year is applied once per year, so the n is 1 in this case. Again, n is 1 in this case, and the time is 5 years. Okay. Let me see. How can I do this? Yeah, let me just use my calculator. Let me see. That's going to be 1.06. Let me try it. Hey Siri, what's 8,000 times 1.06 to the power of 5?
The answer is 10,705.80.
705 and 80 cents. 705.80. Okay. So with compound interest, and in the previous one she had 1040, so she got a little bit more with that one. How much interest will she receive? So then basically this future amount minus the principal. So then if we said that minus 8,000, so for B, basically we subtract, what is that, 2,000? So then 2,705.80 cents. That's the interest earned with the compound interest. Okay, let me see. Moving along. Let me see the time. This class goes. What time do we get out? We get out at 3:15. We're gonna try to take advantage of the time. We need to kind of push. So this is the formula that I used. I used the compound interest formula. Okay. Again, A is going to be the amount after T years. P is the principal or starting amount. R is the annual interest rate expressed as a decimal. N is the number of compoundings, number of times the interest is compounded in a year, and T is the number of years. Okay. I usually like to have you guys do this, but you see, if $100 is a deposit into an account that pays 5% annual interest, find the future value after 1 year if the interest is compounded in these varying amounts. Let's see. So then for the first one, the future amount is going to be the principal, which is what, $100, 1 plus the rate, which is 0.05. If it's annually, the number of compoundings is once per year. And then once per year times 1 year, right? Yeah. So then 1.05, 100 times 1.05 is $105. So the first one is 105. Okay. Semi-annually. So I'm going to call the first one A1. I'm going to call this one A2 for semi-annually. So that means, again, we start with $100. 1 plus the rate is still 0.05. But now the number of compoundings are twice in a year. Again, twice times 1. Hey Siri, what's 100 times 1.05 squared?
The answer is 110.25.
So this one generates $110.25. Right? So all we're changing is the number of compoundings with each step. Quarterly. How many times do you think that the interest is applied if we do it quarterly? Right? We think of quarterly, that means 4 times in a year. Right? So then we're going to do this, this, this. Now our n is 4. Again, 4 times 1. Uh-oh. You know what? I think I missed something there. I got to go back. I'm trying to do this audibly. Yeah, we definitely made a mistake there. Let's back up. Okay. Got to think about it. 0.05. I'm going to have to use a calculator. Yeah, I'm just going to crunch the number. Because I'm trying to use Siri, but it's going to be too much. And I definitely missed something with that last one. go back. I'm gonna just use my calculator here. This one. Reload, refresh. Okay. So if I do 100 parentheses 1 plus 0.05 divided by 2 squared. Okay. And so actually, okay, let me show this. Let me show how I'm going to do this instead. Let me do this. So I have a faster way instead of typing it every time. All right. Let me do this really quickly for these guys that have not seen. I need to go through and update my attendance. Okay. Let's do this. Okay. Reload and refresh. So on my Texas Instrument, so I'm going to do it a little bit differently. So the only thing that's changing with each of these is our number of compounding. So we can actually make a formula or a function. I'm going to say 100 times 1 plus 0.05 divided by, that's changing, so that's our variable, so I'm going to say divided by x, and then to the power of x. Okay? Because all the years are 1, so the number of compoundings is the only thing that's changing. Right? So then I'm going to quit, and then I'm going to call on that function I just typed in. And so for instance, the first one, our compoundings was 1, so we should get $105. The second one, I knew I made a mistake, so we should get something other. Now the number of compoundings is 2. Yeah, 105.06. 105.06. So the next one, the number of compoundings is 4. So now I'm going to let the compoundings be 4. 105.09. If it's monthly, then that means it's 12 compoundings in a year. And so we're going to just let n be 12. 105.12 approximately. These are all approximations. And then daily would be 365. Okay. And so if we let x be, or n be 365, okay. So you should notice a pattern. You should notice a pattern the more compoundings we do in a year, right? The more compoundings we do, the more return we get. Okay. So in the following computations, P was 100, R was 0.05, only N changed, right? So we changed N each time. Okay, and I think we got all these results. So then I don't want to, another type of compounding that we have is called continuous compounding. Suppose the interest was continuously being applied, right? So then A is going to be the amount after T years, P is the principal, R is the annual interest rate expressed as a decimal, and T is going to be the number of years. E is going to be like a function in the calculator, kind of like pi. E is a function in the calculator. So find the amount when the principal of this is invested at this rate, compounded continuously. So continuous compounding, we use the formula, I call it PERT, A equals P e to the RT. It's like the PERT formula. So the principal was 8,300 times e to the power of the rate was 0.075 and the time 8 years. Right? So then we just put that in the calculator. So then we're going to do 8,300 times e to the power of 0.075 times 8, 15. I'm going to say this is approximately $15,123.59. Okay, let's see the time. Yeah, I think we go until 3:15. Let me go for like another somewhere between 5 and 10 minutes. We might be able to finish this. We're actually almost done, so we got a good rhythm going. 15, 409.83. Let me see. 825. Oh, and 3 months. I didn't see the 3 months. Okay, so 3 months we have to convert to years. So then 3 divided by 12 is 0.25. So yeah, I didn't see the 3 months part. Right here, 8.25. Right, and let's fix this. And so then here, what I'm going to do, I'm just going to call on what I had before and just include, I want to insert that 0.25. It's going to be 15,409 and 83 cents. Okay. Again, I just didn't see, moving a little bit quick, didn't see the 3 months. Okay. 4983, okay. So, so now we wanted to introduce this notion of the natural exponential function. Let me see. I think we can finish this out. With the base e, it's so prevalent in the sciences that it's often referred to as the exponential function or the natural exponential function, right? So e to the power of x. We just did an example on it. So base 2, 2 to the power of x we see in blue, 3 to the power of x we see in green. So e is somewhere between, e is a basis between 2 and 3. But it's a little bit, notice it's a lot closer to 3 than it is to 2. So E is like a 2.7 something. Use transformations to sketch the graph of this. Okay. So let's do a quick sketch. First, let's list out our transformations, right? So if we work our way from the inside to the out, the innermost transformation, we said that -1. That's going to move the graph. The first transformation, we should go to the right by 1 unit. Then we have that +2, so that should move it up by 2 units. All right. So, say this is the positive x, say this is the positive y, and say this was just the graph of a general exponential function, right? So then if we use those transformations, they're all rigid transformations. So, and we're going to follow, let me get rid of this. Let me do something a little different. So let me see, kind of like this. I want to have a point there. All right, this is the graph that we're gonna follow that point 0, 1, right? So then if we go to the right 1 and up 2, that's the graph. And the horizontal asymptote is now here. And let's do this other one instead. Now we have a horizontal asymptote. Actually, I can do this. Like this. Then I want to go style. And, one of these guys. I think that'll work, right? Horizontal asymptote, right? It's just up. Oh, it's been moved up by 2. Okay, let me see the time. Okay, I think we're okay. We're almost done. So we went right 1 and up 2. Okay. So then, say we want to model exponential growth and decay. This is essentially the same thing we've been doing. It's just written a little differently. A of t is going to be the amount after some time t. A naught is going to be the initial amount. K is going to be the growth rate. If k is positive, it's the growth rate. If k is negative, it's the decay rate. And t is going to be our time. Okay, I think this might be the last one. Okay, well we got a couple. So in the year 2000, the human population of the world was approximately 6 billion people, and the annual rate of growth was about 2.1%. Using the model on the previous slide, estimate the population of the world in 2030 and 1990. Okay. So we're going to use A of t equals A naught times e to the kt. Right? So, okay. Let me see. So if we let 2000 be 0, then if we want 30 years later, we can do A of 30. Right? That's not a 30. A of 30. I'm watching the clock. About to later. We got a solid 10 minutes. Let's take advantage of it. A of 30. So the initial amount in 2000, it was 6 billion. So we're just going to say 6 for 6 billion times E. The growth rate of growth was 0.021. And again, the T in this case is 30. Okay. And we're just going to crunch that number. So then if we say 6 times e to the power of 0.021 times 30, 11.27 billion. So at that rate of growth, we're anticipating it to grow to 11.27 billion people. Okay, we'll see. That's A. And then B, if we're doing 1990, so that's like 10 years earlier, so we're going to do A of negative 10. That's going to be 6 times e to the power of 0.021 to the power times negative 10, right? So we're just going to do the same thing, but instead of 30, we're going to change this to negative 10. 4.86 billion, approximately. Billion people. Okay, let's see how do we do. Again, I'm watching the clock, trying to get you guys out of here to honor the time. We're still good on time. 11.27 and 4.86. 11.27 and 4.86. Okay, so again, that's just based on the model. I've heard, now I don't know the truthfulness of it. I haven't researched or looked into it. I heard something recently the other day. It was like, you could fit all 7 billion people in the state of Texas. I was like, is that true? Like, what does that look like? Are we like jammed, or like do we have space? Like, what does that look like? Is that for real? I don't know. But you can look at it, you know. You can research it yourself and decide for yourself. I think the answer is wrong, which is what I didn't want, but that's okay. We buy a fishing boat for $22,000. Our boat depreciates exponentially at this growth rate. Find the depreciated value. So the only difference is we're still using the same formula, but now our exponent is negative because we want decay rate. We want the decay rate. So the initial amount was 22,000. Decay was 0.15. 15% is going to be 0.15, and it's still 5 years. And again, we have to make sure that exponent is negative. And again, if we buy a boat, we expect the amount to go down. Right, and we get this. Okay. All right. So we actually did finish 3.1 in one lecture. Okay. So then, what that means is that on Thursday we'll go ahead and do the last lecture. I think it's like section 6.4. All right. Okay. I might just go ahead and make everything available, especially depending on what times, if everything, like depending on when we're supposed to finish. And I think I already have it scheduled to open up at a certain time as well. So anyway, I'm available if you guys have questions. Otherwise, if there aren't any burning questions, I'll see you guys on Thursday. Thank you for being awesome. Until next time.
Thank you.
Yep.